surface of the hepatocytes, I'm having this G protein coupled receptors. So this GS coupled receptors, it is what? Glucagon. So when this glucagon is working, it is responsible to activate G protein, enzyme, second messenger, protein kinase pathway, right? So increase in adenylate cyclase and increase in cyclic AMP. So that's what it is responsible to increase the activity of cyclic AMP response elements binding protein. Its binding protein has to migrate inside the nucleus. And there it was binding to cyclic AMP response elements. On the other hand, we have cortisol. Cortisol, which is a stress hormone of the body, it has the receptors which are intracellular. Remember the receptors, they are having what? Zinc finger motifs, responsible to regulate the production of a gluconeogenesis enzyme, PEP carboxykinase, right? So this is a very classic, important question. Remember that the cortisol plus the receptor, which are zinc finger receptors, this is the hormone receptor complex form. And this hormone receptor complex migrates inside the nucleus. It has to bind to glucocorticoid response element, GRE. Whereas the CREB, which is there, which is cyclic AMP response elements binding protein, it migrates and binds to cyclic AMP response elements. And what happens, these both are responsible to enhance the gene expression of PEP carboxykinase. It is responsible to convert oxaloacetate to phosphoenolpyruvate.
PEP.
Right, and that's why we say either your glucagon or your cortisol, both are increasing PEP carboxykinase, because the phosphoenolpyruvate eventually will go in the process of gluconeogenesis, because it will the steps will back up. Remember, phosphoenolpyruvate, 2-phosphoglycerate, 3-phosphoglycerate, 1,3-bisphosphoglycerate, glyceraldehyde-3-phosphate, and then glyceraldehyde-3-phosphate is an isomer of dihydroxyacetone phosphate, which would give rise to fructose 1,6-bisphosphate, and then fructose 1,6-bisphosphate was rate limiting enzyme of gluconeogenesis.